example 2. If we're looking at using the same function, f of x equals 3x minus x squared, same boundaries, a equals 0 to b equals 5, find the value of the sum. So notice the difference here. This is asking us for a sum from I equals 1 to 10. This 10 is telling me my n value. Really, that's the number of rectangles, if you think back to where the formula came from. And it's the area of those rectangles that we are summing up. So I just did a quick sketch of this parabola. And if we look at our boundaries, we're going from 0 to 5, okay? And they want me to fit 10 rectangles in here between 0 and 5. Well, what would the width of those rectangles be? So our change in x would be b, 5 minus a, over, now I know n is 10. So 5 on 10 is 1/2. So I would be drawing rectangles that are a half wide throughout this. Okay, so here's my rectangles going up until I hit, it's not perfect. Okay, and so I should be fitting in 10 rectangles. I'm not, that one should have gone further. You get what I'm getting at, okay? So we should have 10 rectangles, 1, 2, 3, 4, 5, 6. Yeah, I think I got 10. And what we should notice is that the width of those rectangles is a half, okay? And so there are kind of a couple ways we could do this question. One, we could kind of go back to the beginning when we were kind of just doing the triangle under the line, very intro to this, and we could just figure out all of these areas and add them up. So we would need to find 10 areas. What we know is that the width is a half, and so if we're thinking about what is xi is a plus the change in xi, so a is 0, so we have this going on. So if we want, remember I is the ith rectangle, so if I want the second rectangle, I is 2 times 1/2, right, would give me, so example, I equals 2, then 2 times 1/2 is equal to 1. That's just telling me my x value here on my second rectangle is 1. Okay, so the first rectangle, the x value is a half. Second one's 1. Third rectangle is 3/2. So you're counting by halves each time. So the first method would be just to add up all of our sums. Okay, so from I equals 1 to 10 of f of 1/2 I times 1/2. Those are just filling in our pieces to the formula. And so we could actually, because that half is a constant, I could actually just use my properties and put it in the front. And then all I have to do is calculate all of those f function y values. Okay, so this is 1/2 multiplied by, well, the first rectangle's x value we just said was 1/2. The next one, the second one, where I is 2, we said was 1. The next one's going to be 3/2. We're just adding a half each time. That's the width of our rectangles. The next x value will be 2. All the way until we get to the last rectangle. So if I do this 10 times, I should get to f5. That's actually my b value, right? That's the last x value is the b value, okay? There it is, there's b. He's going to be the last one. And in between there, I have 10 values. Now, I didn't write them all out. So now this is a little bit tedious because now you have to go to your function and you have to go 3 times 1/2 minus 1/2 squared. That's just the first one, plus 3 times 1 minus, not 1/2, sorry, that was the last one, minus 1 squared plus, and all the way until you get to x is 5, so 3 times 5 minus 5 squared, and you add those all up and multiply by the half in the front. Okay, this is just reminding us, this comes from the function f of x is equal to 3x minus x squared, and I'm just filling that in, and I have to do it 10 times with the 10 different x values. And then once I do that and sum it all up, I get that this is equal to, equal to 1/2 times, okay, so if you wanted to know what some of these values are, I wrote them out. 1.25 plus 2 plus 2.25. I actually wrote them all out. Plus 2 plus 1.25 plus 0 plus negative 1.75. Then I have a minus 4, minus 6.75. This is adding negatives, and a minus 10. And this is equal to negative 6.875 after you multiply by that half in the front. Okay, that's the answer to the sum of the 10 rectangles, and it's not an area, it's just what the integral would be equal to. Okay, the second option, and I didn't give myself enough paper to do it, the second option, I have a blank page at the end, so we'll go there. The second option, so this is example 2, the second option would be that we actually built a formula for this on the previous page. We knew that the sum formula for our function came out to be, now I'm writing shorthand here, so f of x, came out to be 75 on 2 multiplied by n plus 1, this is the simplest one, with the n's canceled, minus 125 on 6 multiplied by 2n squared plus 3n plus 1 on n squared. Okay, so this expression came from example 1 before we took the limit. Okay, so after we had dropped our sigmas with our I formulas, but before we took the limits. Okay, well, we're not needing to take a limit because we actually know that n is equal to 10. So we could just use this formula. So because we've done this function already, we could simply use that. It is an alternative. I mean, if you had n was 100, I certainly hope you wouldn't want to do 100 calculations. So you could make your formula first and then go ahead and throw in your n value. Okay, that's the alternative method to calculating all of the separate calculations, which is very tedious. And so after we put in that n is 10, we get, it looks like I have 165 on 4, subtract 385 on 8, which is equal to negative 55 on 8, which is approximately, not approximately, sorry, is exactly the same as what we got. It's equal to negative 6.875, which, you know, I'm all about the exact value, so I should have written the other answer as a fraction. Tisk, that I never did. Okay, so that's an alternative method to doing it when you actually have an n value. You can still go about and fill in your sigma notation, go ahead and expand it as if you're doing the limit question, but then don't evaluate the limit. Okay, pause and put your n value in. Okay, so back to where we were. Okay, so I'm just going to rewrite this answer as our fraction because, of course, we prefer fraction answers. All right, so In general, if a function f takes on both positive and negative values, then we can actually interpret the integral as a difference of areas. What does this mean? We're not actually calculating area. We're calculating the integral as a difference of areas. Okay, what is that getting at? So area 1, A1 is the area above the x-axis, and A2 is defined as below the x-axis. So if we take that parabola we were just looking at from the boundary 0 to 5, we can clearly see that we have two regions. We have an area above and we have an area below. Okay, now if I only wanted the area, then we would go A1 plus whatever area 2 was, that integral, we would need to take the absolute value of it, right? That would give me my area. Now I've put these down as areas. But if I'm actually calculating the integral, okay, the integral, this is an integral, not area, okay, integral. We're interpreting this as a difference of areas, okay? Then if you take your above region area and you subtract your below region, then you get the answer to the integral. Okay, so if I want to know what the integral's answer is, not interpreted as area, you take above minus below. Okay, so a little bit tricky, but that's how we can get negative answers, because obviously in this particular circumstance, the area below the x-axis is actually bigger than the area above, and that's why we're getting a negative answer to the integral. So if we're interpreting it as the integral, it's a difference, okay? We're subtracting. We are still calculating areas and then subtracting to get the integral answer. Okay, so what does this mean? So just looking at this other diagram. So what if I knew that the areas above were all a little bit different? Okay, they don't look exactly the same. Let's pretend that this first region is 10, the second region, I don't know, is 9, and the third one is 8. That's probably not true because, you know, whatever. And then what if we said down below we had this section was -4 and this section was -5, okay? And it's negative because it's below the x-axis, okay? So to answer the area question, we would have said the area above would be 10 plus 9 plus 8, which is 27. And then we would have calculated the area below, and we would have added those two numbers together. We would have got -9, but we would have taken the absolute value of that, and we would have said the area below has to be, if it's area, it has to be positive. So we would take the absolute value of that negative, and then the total area, right, the total would be, added those two together, would be 36 units. Okay, that's total area. This is saying, what if we wanted you to calculate the integral, not the area, but use your area numbers to do so? Then they're saying that the 27 would represent a 1. Okay, actually, let's use a different color. Okay, and that the 9 would represent A2. So if I wanted to know the integral from A to B of whatever this function is, kind of looks sinusoidal, but not sure, it doesn't matter, then I can take the area 1, the above area, and subtract the below area. And so I would get 27 minus 9 is equal to 18. And sorry, this should say units squared. This is area. This is the answer to the integral, the definite integral from A to B. Okay, and you have to be really careful to pay attention to the difference in the question. Is it asking you to give the area find the area, determine the area, or is it asking you to just determine the integral? If this is asking for the integral, then negatives are allowed. It would be the same as me just saying, this is 27 plus negative 9 is 18, okay? But this formula is talking about using the difference of areas to interpret the integral. Okay,